Hi, my name is Brianna Poon, and this is my lab report for Lab 5 in Physics 2211. So the purpose of this lab was to analyze the motion of a fallen Slinky dropped from rest, and to do this I used Tracker to analyze the actual motion of the object and then created a model that illustrates the theoretical motion. And then I compared my observed data with my computational model data to analyze the accuracy of my results and also explain the reason behind the Slinky's movement. So some fundamental principles I used were Newton's second law, which states that the net force acting on an object equals its mass times its acceleration. And then from this, I also got the position and velocity update formulas. And then I also used the gravitational force, drag force, and tension force formulas, which I used in the calculation for net force. So my procedure involved using the Tracker software to analyze the motion of a fallen Slinky, particularly the bottom part of the Slinky while it's being dropped. And then my system was a Slinky, and my surroundings were everything else. And then I used the initial conditions from the Tracker data to create my computational model. And some assumptions in place here are that initial velocity is 0 meters per second, and also that there exists a drag force that is opposite in direction of the object's motion and proportional to the square of the object's speed, and I'm only analyzing motion in one direction. And so here's a picture of my Tracker analysis. I wasn't actually able to attach a video of it, but what happened in the video was that as this was dropped, the bottom part of the Slinky remained still until this top part fell down to the bottom part, and then it all fell down to the ground. So the data that I got from that, I have my initial conditions here: position, velocity, start time, end time, and frames per second, which I use as my delta t. And then I put that into my initial conditions of my code, along with the proportionality constant for the drag force formula here. And then here is my actual process of iteration for the computational model. On the left here is what happens to the bottom of the Slinky before the top meets it. And then on the right here is when the top of the Slinky meets the bottom, and then it all falls down to the ground as one unit. And so here's a graphical comparison between the data of the two, where the orange line is the Tracker data, and then my blue line is the GlowScript data. And so, as you can see from that graph, the observed data and the model start off on a similar path, but as the model position begins, time progresses, the model position begins decreasing more rapidly than the observed data, and this shows evidence that there may be another force present acting on the object besides gravity, or that I just didn't calculate drag force correctly, or accurately, I should say. And so some sources of error, again, drag force calculation may not be 100% accurate, and this is probably because the Slinky is more of a coil wire than a solid mass, which makes the effects of drag a little more complicated to model, I guess. And also there's human error. I manually inputted the points of mass in Tracker, so they might not be 100% perfect, especially since the video was kind of blurry. And also I had to estimate the mass of the Slinky and the reference points in my Tracker model because I didn't have any of that information when I was analyzing the video. And so some questions for consideration here. Does the bottom of my model Slinky stay stationary just like in the video? And the answer to this is yes, it does remain stationary, and this was intended because I wanted to model I wanted my model to accurately reflect how the Slinky moved in the video, and that's why I had two iteration processes in my code. And without this, the model would simply reflect a normal falling mass, which wouldn't be an accurate representation of what's happening to the bottom of the Slinky in the video. And so more on that, why does the bottom of the Slinky stay stationary? And this is because in the beginning, there are two forces that are acting on the bottom of the Slinky. There's tension force from the rest of the Slinky, and there's gravity that's pulling down. Before the top of the Slinky meets the bottom of it, the tension force and the gravity force cancel each other out, which results in zero net force on the bottom of the Slinky. But once the rest of the Slinky falls to the bottom and meets the bottom, the tension force becomes null. So then gravity again takes over, and then it falls normally to the ground. And so some other applications of this effect are vibrations in like other ways. So like for example, when you hit a tennis ball with a racket, the vibration that you feel when you hit the ball is actually delayed from what you hit when you hit it. And this is because like a similar effect to how like the slinky doesn't the bottom of the slinky doesn't like fall normally until the top of it meets it. So that's the end of my presentation, and thanks for listening.